Okay. Okay, thank you. Welcome to GADEPS. So today we have Ignacio Barros, who is going to talk about irrationality of moduli space. Okay.
Thank you. Thank you for having me. And yeah, this is everything I'm going to talk about today is joint work with Daniele Agostini and Juan Wen Lai. Okay, here we go with the problems. There you go. Okay. All right. So I will break it in four. Yeah. So first, talk a little bit about the history of this problem and motivate it. Then sort of place the question, the main question, and then talk about some results and finally a little bit about what goes into the proof. Okay, so this is the elementary part, yeah. So a Riemann surface, yeah. That's a genus 4 Riemann surface, right? A Riemann surface is a one-dimensional, compact, complex manifold. And topologically, right, they are classified by the genus. Right? So this is genus 0, the Riemann sphere, genus 1, genus 2. Right? So a Riemann surface is that, together with a complex structure on it. And this is Riemann, a photo of Riemann, and this is the Riemannstrasse in Berlin and the Riemannstrasse in Leipzig. And actually, I keep it like that, but I was told that this Riemannstrasse, the Berlin one, is attributed to a different Riemann. But anyhow, but this one is for sure. Bernhard Riemann.
Ignacio, are they main streets? Because in Paris, I found the Cauchy. It was very small street.
Yeah, no, these are also tiny streets.
Okay.
But yeah. We'll talk about that later. But you know, like there is a small sign for the. Okay, let me not. All right, we talk about it later. Okay, so in 1857, right, Riemann publishes in Crelle, yeah, this paper. That's the title of the paper, Theorie der Abelsche Funktionen. And in this paper, there is this paragraph in the middle of the paper, which it has been one of the most influential paragraphs ever written in the history of mathematics. This is just one paragraph where he conceives a space that parameterizes all Riemann surfaces of given genus, gives some sort of plausibility argument for what the dimension should be. P here for Riemann is the genus, and gives a name to this space. Welche die Modul diese Class genannt werden sollen. Yeah, so this says the class of parameters that parameterize this space should be called moduli. Yeah, so this is the moduli space of moduli. So this is MG, yeah, the moduli space of curves, right? Parameterizes all Riemann surfaces of genus G. Yeah, so every point is a box, right? That you open it and you see a Riemann surface. And what I find very remarkable is that we needed more than 100 years to actually properly define this space, right? It was defined as a complex manifold by the work of Teichmüller in the 50s, and then as an algebraic variety in the 60s by Deligne and Mumford. And I want to talk a little bit about the geometry of this space. So this is a genus 2 curve. Yeah? And we know this is sort of one of the first exercises, right, that you do in an algebraic geometry course is to show that every genus 2 curve can be realized as the closure of an affine equation of this shape, right? So this is a degree 2 map. So let me just say it like that, right? So so in other words, if I fix, we are over C, right? So this polynomial determines my hyperelliptic curve, right, of genus 2. So if I fix the 6 roots, right, then this induces what is called a unirational parametrization of the moduli space. So if you give me 6 roots, 6 complex numbers. You can choose them freely. Then I can produce for you an hyperelliptic curve, right? So yeah, so this is this. You cannot choose them totally free, but I mean they move freely. Yeah, you can perturb them freely, right? And then you actually recover all Riemann surface of genus 2, or the general one. Yeah. So and yeah, this is simply by prescribing these 6 complex numbers and forming the isomorphism class of this 0 locus, right? And you can do the same for genus 3. Right, so let's just not talk about the closure yet immediately, right? This is a degree 4 homogeneous polynomial in 3 variables in P2, right? So a general genus 3 curve, actually a non-hyperelliptic one. This is also an exercise, right? And it's simply by looking at the canonical embedding, right? So a general genus 3 curve can be realized as the vanishing of a degree 4 polynomial homogeneous in 3 variables. And so again, right, so then prescribing such polynomial is simply prescribing the coefficients of all the monomials, right? So this induces what is called a unirational parametrization of M3, which is I give you these 15 complex numbers, right? And then you produce for me a genus 3 curve. And the general genus 3 curve can be obtained in such a way, right? So I can walk through this space, M3, by moving 15 parameters freely, right? So I have a map. Yeah, and so the map is exactly this, right? And you can keep on playing this game. And actually, yeah, so for low genus, they are elementary, but this problem becomes very fast, very, very complicated. But anyhow, so for genus 4, a general genus 4 curve lies on a quadric and a cubic. So it's a complete intersection of 2 polynomials, one of degree 2 in 4 homogeneous variables and one of degree 3. Right? So again, right, this induces a unirational parametrization, and this n is whatever coefficients I need to prescribe to give you this and this polynomial. Right? So yeah, and then the fundamental sort of theorem about MG is that this game actually stops. So this was believed for many years to be true for all genera. You are able to write that so that MG is unirational, admits a unirational parametrization, right? For all G. And this is not true. So, okay, so the fundamental invariant in birational invariant that measures complexity is the Kodaira dimension. Yeah, so the Kodaira dimension is a number that can be either 0, 1, 2, all the way up to the dimension of the variety, or negative. Yeah, that we declare it. We declare it to be minus infinity so that easy addition formula works. But anyhow, so but still, 2 varieties that have the same Kodaira dimension, they can be quite different from a birational point of view. It's a very coarse birational invariant, the Kodaira dimension. So for instance, among those that have negative Kodaira dimension are those that are rational, right? Meaning birational to a projective space. Those that are unirational, meaning those that admit what we said before, admit a dominant map from a projective space, and uniruled, right? And this is, of course, this, I mean, every rational variety is unirational and every unirational variety is uniruled, right? Uniruled means that it can be covered by rationally by rational curve. Through a general point, there is a rational curve passing through. Yeah, and the proof of this fact, sort of, if it is uniruled, it has to be negative, is very easy. It's because if you have, so this measures more or less how many differential forms your variety admits, right? So on any such, if you restrict it to a P1, it has to have poles, right? Or be trivial. So P1 doesn't have holomorphic 1 forms. So if P1 covers your variety, right, then that forces whatever you chose at the beginning to be 0, right? Okay, and on the other side of the spectrum, we have those that have maximal codiral dimension, and these are called varieties of general type. And this is essentially a fancy name to say we don't know much about it. So but we know, for instance, that they cannot admit a unirational parametrization, right? So, and yeah, as I was telling you, right? So this is a theorem of Severi, more than 100 years old. So, which is kind of cool, like to put on a talk theorems that are more than 100 years old. MG is unirational for G up to 10. Yeah? And then it became known, even though Severi didn't conjecture, but it became known as the Severi conjecture, that MG should be unirational for every G. So in particular, the codiral dimension has to be negative. So this is Severi. And yeah, there are quotes. Okay, so this is a quote of Mumford. Yeah? So whether more MGs for G greater or equal than 11 are unirational or not is a very interesting problem, but one which looks very hard to, especially if G is quite large. And this is Mumford, and then here is the theorem. Yeah? This is Harris-Mumford, and then Eisenberg-Harris. MG is actually not unirational. Not only that, it's much worse. MG is of general type if the genus is at least 24. So,
Ignacio, you have a MG bar and MG, so I think you are talking always about the compactification MG bar.
It doesn't matter because it's a birational invariant. So the codiral dimension is all, these are all birational considerations.
Okay.
Yeah. Okay. I mean, the codiral dimension is defined for projective things, but it's a birational invariant. So actually it doesn't matter what do you mean by bar, right?
Okay.
As long as it's projective, yeah. So the question here is, so how irrational, okay, we know that is not rational. It's certainly not rational. It's not even unirational. It's not even uniruled. But then how irrational is it? Yeah, and that's the content of that's the question. So, and also I need to tell you how I measure this. So, and there is a sort of, not a parallel in time, but a theoretical, I mean, in terms of theory, like a parallel story with K3 surfaces, but it's much modern. So a K3 surface, right, is a complex two-dimensional manifold with trivial canonical class and simply connected. Okay. And then not all of them are projective, admit an embedding to projective space, but some of them do. And then, so those are algebraic, these form a moduli space. Yeah, this is the moduli space of primitively polarized K3 surfaces. So this is a K3 together with an ample line bundle. And I fix the degree. Yeah. And then, this G here is related to the previous G actually, because if you take this ample class, say it's very ample, you see the K3 in a projective space. This projective space is of dimension G. Yeah, H0 of this line bundle is G plus 1. And if you take a linear section, that is a curve in PG minus 1, which is canonically embedded and of genus G. Yeah, so that's the link. Okay. And then, so this is a vast sort of, this major part of Mukai's work. This is a series of 5 or 6 papers, is this, right? This is the analogous of Severi theorem for MG, right? FG is unirational for G up to 12, and then this genera, 13, 16, 18, 20. And this has been upgraded by Farkas and Verra in 18 and 2020, where they added here 14 and 22. Yeah. But you see there are many more open problems here in this side of the story, right? It's more recent. And then there is an analogous theorem, which is FG cannot be always unirational, cannot be even uniruled because it's of general type as soon as the genus is, or the degree, right, is big enough. Okay. So again, Fg is not rational, it's not even unirational, not even uniruled. Yeah. But how irrational is it? Yeah. And this is, and let me say before I go into what I mean by how irrational, so for both, for Mg and Fg, this has a very sort of deep implication, which is if you give me, say for Mg, genus, if G is greater or equal than 24, meaning if Mg is of general type, if you give me a curve of genus 24, right? And you can write it, you can tell me, look, yeah, it's pretty easy, right? I take, I don't know, a polynomial of degree 4, 5, 6, 7, and 10 in P, I don't know what, I intersect them. And if I choose them, you know, the polynomials general enough, I get something that is smooth and of genus 24. Then this result implies that that curve is very, very special in the moduli space, right? You cannot produce a recipe to write down an equation for a general genus 24 curve, as we did before for genus 3 and 4, right? So, and actually has more consequences, but this is, this is sort of just to appreciate somehow like the depth of the theorem. Yeah. Okay. So how irrational? Yeah.
Before going, all these proofs of rationality and irrationality, it's theoretical, or they write down explicit parametrization and so on?
Well, some of them, I mean, I gave you some concrete parametrizations. Yeah, that's a good point. Actually, yeah, Mukai's one, these are concrete, fairly concrete. I mean, it's not just that it shows that it's unirational, it gives, it writes this down as some linear space quotient by some group. So it's a concrete description. Yeah? So for instance, I mean, my favorite is genus 8. Yeah? So a general K3 can be seen as some linear section in a Grassmannian 2,6 embedded in P14 via Plucker. And then you get the general one by varying, right, this linear section. And then you need to quotient out by automorphism group of this Grassmannian. Right? So then it tells you more, right? But then, for instance, the last ones, these 14 and 22, they are not. They are via, these are produced via, there is a dictionary between K3s and special cubic fourfolds. And this is done on the cubic fourfold side of the story. But yeah, I mean, yeah, by rationally, you know, actually, I mean, I should maybe take that back. Rationally, they are maybe concrete. I don't know. I don't know. Yeah. Yeah. So, all right. Okay. But then the general type is simple. Yeah. Okay. So let me just say, yeah, stop there. All right. So what do I mean by how irrational? Yeah, so this is a sort of a circle of ideas that is actually sort of old in the literature, but it had some revived interest in the last years, and goes by the name of measures of irrationality. Yeah, so I will introduce two. There are various, but two of them, sort of the finest and the coarsest. So the finest is the degree of irrationality, and this is very elementary to define actually. It's the smallest possible degree of a map, rational map from my variety to a projective space, dominant. So for instance, if this number is 1, this means that the variety is rational. If this number is 2, it means that by rationally you can this is a 2-to-1 cover of a projective space. If it's 3, and so on. Yeah. And then the other one is called the covering gonality, and this is the smallest gonality such that a general point, so through a general point there is a curve of gonality C passing through it, meaning it's the smallest possible gonality such that by rationally you can cover your variety by a family of curves of that gonality. And the gonality of a curve is simply the smallest possible degree map to P1. So the gonality of an hyperelliptic curve is 2, right? The gonality of a trigonal curve is 3, and so on. It's clear? So the covering gonality is 1 if and only if my variety can be covered by rational curves. It's 2 if it cannot be covered by rational curves, but you can cover it by hyperelliptic curves, and so on. Yeah. So yeah, so this is the same what I was saying, right? This is the same as saying that there exists a curve fibration where the general fiber has gonality C and this map is dominant. And yeah, as I said, the degree of irrationality is 1 if and only if the variety is rational. The degree of the covering gonality is 1 if and only if the variety is uniruled. And they are related, right, by this inequality. So you have a map that realizes the degree of irrationality. Then if you take a P1 downstairs, right, then the preimage of that P1 is going to be a curve of gonality at most the degree of irrationality, right? So yeah, this is the question. So, and yeah, I should say, I mean, maybe, I don't know, for like students on the audience, but it is well known that actually detecting rationality is a very difficult problem in algebraic geometry, right? Deciding whether a variety is rational or not. And the most famous example is, for instance, cubic fourfolds. Yeah. So a cubic fourfold, this is simply a polynomial of degree 3 in what? In 5 homogeneous variables or something, or 6. We don't know which ones are rational and which ones are not. And yeah, and if you there are many conjectures there. And so in principle, it's a bit hopeless to actually. I mean, yeah, it's naive to expect to give a full answer to this, right? Like just like this. I mean, we start with bounds, yeah? And let me tell you what is known for MG. So the only thing we have for MG, we have nothing for the degree of irrationality. I mean, we know that when G is large, this cannot be 1 because it's not rational, but that's it, right? And we have only a bound for the covering gonality. So this is the Hurwitz space. This parameterizes maps from a curve of genus G of degree D to P1 simply ramified. Okay? Isomorphism classes of that. Yeah, there is a moduli space, it's well studied, it's yeah, quite classical actually. And this, so you have two forgetful maps, right? The one that if you have a map, you forget the map and just remember the curve. This goes to MG. And this map is actually dominant if the degree is greater than this. This is the gonality of the general curve of genus G. Yeah? So at some point it becomes dominant. Yeah, for instance, if I put here D equals to 2, the image of this map is the hyperelliptic locus. Yeah? And there is another map that forgets the curve and remembers the P1 together with the image of the ramification points. Right? So this goes to moduli of genus 0 curves, P1, together with, I mean, a map of degree D from a smooth curve of genus G is ramified at these many points, right? By Riemann-Hurwitz. So it has all these markings and they are up to order. Right? In principle, I have a ramification divisor. I haven't declared any order on them. So this map is finite, yeah? And I should say these numbers, so okay, these numbers are called Hurwitz numbers, and we don't have a formula for them. Yeah? There is quite some theory behind them. And they count, if you fix P1 and you put this many points, how many genus G curves can be realized as a cover ramified over those points, right? And this has to do, this is actually an elementary sort of counting question because so declaring what the curve will be is the same as declaring the monodromy on top of each point, right? So this is actually a finite count. It counts subgroups of Sn that act symmetrically, that act transitively on the fibers, and then there is some compatibility condition.
Just a comment, Ignacio. The generating function of these are quasi-modular forms. This is one of the other topics that which appeared in this seminar.
There you go. Okay. So that's lovely, but there is no, if I give you, my point is, if I give you this number, you cannot write for me down the formula. Or can you?
For the generating function, the works of digraph Kaneko-Zagier. You can write closed formula for the generating function, fixing G and varying D.
Okay. So this is actually, I think I will talk about this, like maybe these are the same people, but anyhow. So this implies in particular that the covering gonality of Mg is bounded by these numbers. Right, because if this variety is rational, this is some symmetric product of P1s, So it's rational, it has a bunch of rational curves. If you choose one, then the gonality of the curve that you see here upstairs is at most this, right? And then this maps dominantly, right? So through a general point here, there will be a curve of gonality at most that, right? So maybe I don't know if this is the paper that you were referring to, but they show Dubrovin, Young, and Zagier, 2017, that if you fix G and make if you fix D and make G grow, this is exponential, and the other way around. If you fix G and make D grow, this is also exponential. But we are interested when G grows, how is the irrationality of this? But if G grows, then D also grows. But anyhow, I think you can use this to actually show that this is at least grows exponentially on G. If I put here, the threshold here, like G plus 3 over 2. And that's it. That's the extent of our knowledge. So then very natural is the question whether one can find polynomial bounds. This would be sort of a radical difference in the nature of these invariants, right? Even though we still don't know if these invariants actually grow to infinity or not. And as you can imagine, producing lower bounds and producing upper bounds are two totally different businesses, right? All right. So this is the result. So we were able to find a universal bound for all G, for modular K3s. So this is polynomially bounded in G. So for every epsilon, there exists a constant such that this holds for every G. And I should remark some things here, but anyhow, so the constant, this epsilon here has to do with the number of Fourier-Mukai partners of a very general K3. So this grows as big O to the epsilon. And that's why it appears here in the bound. And the 14 has to do with some, I will tell you about it, I hope. We still have time. Okay, so this is, sorry. I can't hear you.
C epsilon goes to 0 if epsilon, C epsilon goes to infinity if epsilon goes to 0. Something like this must happen, no? Or
Sorry?
If epsilon goes to 0, C epsilon will go to?
We don't know. I mean, it would be great to prove that C epsilon is bounded, then I can get rid of the epsilon, right? But we don't know. What we have is that if you fix any epsilon as small as you want, then I can do this. Actually this C epsilon, I mean, maybe if I tell you a bit about the proof, maybe you will come up with a bound for C epsilon, but because it comes from the world of modular forms, which is a world that I'm certainly not familiar with. I mean, we had to sort of go way outside our comfort zone to prove this theorem. So the second one is this, is there are three series of infinitely many G's, so G and D, this is, so the degree of the K3 as embedded via the polarization, right, is 2G minus 2. So if D satisfies this, that, I mean, it's not instructive actually to know this, right? But okay, if D is common to 0 or 2 mod 6 and not divisible by blah, 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 blah. Or if this holds, or if for a fixed n, this is a square, then there exists a constant such that this polynomial bound holds. And of course, here, if I fix an n, the constant depends on n. So I'm providing you actually infinitely many, infinite series of these, or G's, for which there is a polynomial bound of degree 10. But the constant depends on which series I am, right? So, because every number can be written, for every number, there exists an n such that the number minus n is a square, right? The point here is that the constant depends on n, Is it clear? I mean, anyhow, I mean, you just need to think, okay, I have an infinite series of these. Actually, they cover all these, but for each series, the C depends on the series, right? So, and then I have a polynomial of degree 10. And the third theorem is actually for modular of abelian surfaces. It's the same story. But this, it's not out yet. But the argument is essentially the same. So this is the moduli space of 1D polarized abelian surfaces. And there is also a special, so you get degree 2 actually if you go to a special series of infinitely many Ds, like all those that look like this. And again, the constant will depend on E. Okay, I hope the statement is clear, more or less. Well, okay. Should we go? So now we go to the proof. Like, is that okay?
The proof. I missed what was D for if G.
It's 2G minus 2. This is the relation between G and D.
So D is always, in this case, it is
the degree. Is the degree of the polarized K3.
So I didn't like it. It's a condition about the genus again, no?
Yeah. I mean, it's just that I don't want to translate it into a condition on G. Okay. Because then there are fractions also, right? But So, or if you want, this is a condition on the number 2G minus 2.
Okay.
Okay. And then, I mean, this, so if maybe some of you, I mean, these series of numbers, I did not certainly come up with them, nor my collaborators. These are well-known series, and this is the degrees for which the K3 admits an associated special cubic fourfold. And these are the degrees for which the K3 admits an associated Gushel-Mukai fourfold. And this is the degrees for which the K3, right? The Hilbert square of the K3 is Hodge theoretic special. All this special thing has to do with the fact that the H2 of the K3 appears in cohomology groups of these objects that I just listed. So, okay, all right. I mean,
So this C number is computable, or it's just theoretical number that exists?
It's a theoretical number, and it comes from the fact that, I mean, it comes from this fundamental result of Hecke, saying that a modular form, right, a scalar valued modular form is in O of the coefficient I is in O of I to the power at most the weight minus 1. So that's what we use. I don't know how explicit that is. But probably not if you have, I mean, maybe for explicit modular forms, you can say something, but for a general modular form of weight something, for the full SL2, right, on then, yeah. Okay. But that would be great, actually, if any of you have some input on that, actually, because I mean, my knowledge in modular forms is very narrow. I'm sort of getting into it, getting the taste of it a bit, but okay. So the main ingredient of the theorem, the universal bound, is something that goes by the name of Kudla's modularity conjecture. I don't know if you had anyone on the seminar talking about this. But this essentially says that special cycles on orthogonal Shimura varieties, I can take a generating series, they arrange on a generating series that is modular with coefficients on the Chow group of the Shimura variety. And this, the codimension, one case of this is known as, it's a well-known theorem of Borcherdt's. And it was conjectured for quite some time. This has been closed in 2015 by Brunier and Westerholm. So this is one person. Yeah. Okay, so this epsilon, as I said, this epsilon has to do with the number of Fourier-Mukai partners of a very general point in Fg. Yeah, so the number of Fourier-Mukai partners that it has, which is the same as, so this is a classical result of Orlov, actually, that two K3Fs are derived equivalent if and only if their transcendental lattices are isometric. And yeah, counting this is the same as counting how many different prime divisors the degree 2G minus 2 has. And this grows at most. I mean, it's actually there are lower bounds for that, but they are all very ugly looking. You know, log of something, and yeah. But you can certainly show this that is bounded by G to the epsilon. Okay, and then, yeah, the question that I always ask, because I have zero input on this, I mean, and I would love to understand it, is can we say something about MG? I mean, there is nothing, there is simply nothing. There is only this thing about the covering gonality. And one sort of fundamental feature that Fg has and Mg doesn't is that Fg, no matter what G is always of dimension 19. Whereas Mg grows linearly, the dimension, right? The dimension is 3G minus 3. So, and this has to do with the strategy that the strategy will be to put all these FGs in one big projective space. That strategy fails from the beginning for Mg. Because the dimension goes to infinity. Maybe the simpler problem is if you fix G and you make the number of markings go to infinity. This also becomes of general type, but can we bound this thing? Okay, so this is, as I was telling you, this is sort of the main idea of the proof. We are gonna put all these FGs in one single big projective space. Yeah? So then once it's in, it has a degree. And certainly the degree of irrationality is less than or equal to that degree, right? Because if you have a variety in a projective space of degree something, you can always take a general linear projection, right? You take a point, you take not a point, sorry, like you take a linear space of the same dimension as the variety, you take something complementary to it, right? And then you take a projection, right? So that thing is, by definition of the degree, is of degree D. It's undominant. So then one has this bound, right? And then the idea is, okay, so this is the work of many people, right? So Borcherdt's and then Hassett for the special cubic in this theorem 2 in the list, right? Then Hassett, then the bar Iliev Manivel for the Gushel Mukai, and then the bar Macri for special hyperkę fourfolds of K32 type, that essentially there is a modular form. I will tell you how this comes up, but there is a modular form of weight 11, certain level, with Fourier expansion at infinity like this. Yeah, and then the degree of these varieties appears here as coefficients. Yeah, this d is 2g minus 2. And once you are there, then you can breathe in peace, right? Because this thing has to be holomorphic at infinity. The coefficients cannot go as nuts as they want, right? So their growth is controlled, and it's actually this, the growth of the Fourier coefficients, right, of a modular form of weight k grows as big O of n to the k minus 1, right? For k, I think k has to be greater or equal than 3 or 2 or something. Okay, so that's roughly speaking the strategy that we follow to prove theorem 2. Okay, so yeah, I mean, maybe all of you know this sort of very well, but
so the coefficient c comes from this modular form that you
the Borcher's one, yeah. So okay, so yeah, exactly. So we are gonna just sort of do an elementary manipulation of Borcher's modular form to obtain the degrees there and to actually get down a scalar valued modular form. Yeah, so a standard modular form. Okay, so all right, so tau is an element of the upper half plane. Yeah, so this is, I don't know, maybe I'm boring you, but on a seminar about modular forms. But all right, so SL2 set acts there, right? And then if you fix a representation of SL2 set, and we actually need, in order to have a reasonable notion of Fourier expansion, we need that it factors through a finite quotient. So it factors through a finite group. Then a vector-valued modular form of weight k and type rho, this representation, is an holomorphic function, right, from the upper half plane to this vector space that satisfies the standard modularity rule, that if you act by SL2, then this appears out as a factor. And then this is a finite dimensional vector space. Okay, so how do I go? Yeah, all right. So let me tell you a little bit about the story of Heegner divisors. So say you start with a lattice, yeah, of signature 2, something. Okay, then for a lattice there is a bunch of sort of canonical objects that come with it that are very important. So one of them is the Weil representation. Yeah, so from a lattice you can fish out first a discriminant group. This is a finite abelian group that is simply by taking the dual of the lattice, quotient by the lattice. And then for this group, you form the group algebra. Right? This is a vector space, it's finite dimensional because this is a finite abelian group. And then there is this very, very concrete representation called the Weil representation. It has a formula for the generators. Yeah? And then, yeah, on the other hand, so okay, from a lattice we can also make out this Hermitian symmetric domain, the period domain, right? So these are points in the projectivization of this tensor with C that have a trivial square, and omega paired with omega bar is greater than 0. Right? And this pairing is the one of the lattice that extends, right? You can simply extend coefficients. So, okay. And then, then we have this group also, right? These are all those elements in O of the lattice, automorphisms preserving the pairing that act trivially on the discriminant. Okay, and then you form the period domain. And this is by work of Bailey and Borel, right? This is a quasi-projective variety. It admits a normal compactification, and the boundary of that normal compactification, known as the Bailey-Borel compactification, has boundary of the boundary consists on curves and points. So this statement is more general, but in this case, the boundary has to do with isotropic subspace anyhow. So it's of dimension 1 or 0. And this space carries natural divisors, right? So you grab a vector in the dual of the lattice, and then you can take the hyperplane, right? So this omega is a quadric, right? This is some sort of quadric condition in a projective space plus this, which is a non-algebraic condition, right? So you can take hyperplanes, right? So we take an hyperplane. And the thing is that if you fix the class in the discriminant group, right? Meaning, so this object mod M, and you take the union of all these hyperplanes, right? Where the square is fixed and the discriminant class is fixed, they do descend to a Cartier divisor. These are known as Heckner divisors. So this descend to actually, a Cartier divisor in this period domain. So so then what? Okay, I have like 10 more minutes or something like that, right? Okay. I'm almost over. Look, yeah, okay. So then this is the theorem of Borchert with an upgrade by McGraw that says the following. So if you grab all these Heckner divisors, and you put them in a generating series here with n, and then you sum over all discriminant classes. So this thing here is a vector valued modular forms with coefficients in the pK. Coefficients, Cartier divisors on the period. Which is, it's kind of spectacular. I mean, anyhow. So it has very strong consequences, this thing. Because this space is finite dimensional. Yeah. So for instance, okay, so if I intersect this, say with a curve in here, right? Then I can intersect all these divisors with a curve. I get a number. That thing lies here, right? Meaning I only need to prescribe, and this is a finite dimensional vector space, so I only need to prescribe a few coefficients, meaning the intersection with a few Heckner divisors to know them all. So that's...
Maybe in this case, Picard group is not finitely generated, no? Is it true? So there are finitely many divisors also involved then.
Yeah, it is. But it is. But this is it is. But this has been very recently established. It is. It is finally generated, and it's generated by this type of divisors. This is a conjecture of Raoul Pandaribande and Davesh Malik. Because the Nether-Lefschetz conjecture. So these divisors have a modular interpretation when you put FG here instead of this PM for the appropriate lattice. And these divisors are exactly those where H2 acquires an extra algebraic class, right? So our Nether-Lefschetz divisors, those where the Picard has not rank 1, but actually 2 or more. And then it was conjectured these divisors generate the full Picard, the moduli space, and it was proved very recently. This is this is Bergeron and Lee and I think 1 or 2 more people that I'm forgetting right now. And actually the Picard rank, so the number is also it has a formula. Okay, so I was telling you, all right. So the fact that this can be compactified to something that is normal, and that the boundary has low dimension. So normality gives me the fact that Cartier divisors are Weil divisors, and then the low codimension means that restricting a divisor on the complement of the boundary is an okay procedure because the codimension is high enough. It's localization sequence, right? So there is a map from the Picard to the class group, right? The Chow one, which is isomorphic to the one of the bound of the Bailey-Borel compactification because the boundary is small. And then I can take the degree here, right? With respect to the Bailey-Borel polarization, right? So this is projective, choose one with respect to that one. So this map induces a map like this, right? Simply by applying it to all coefficients. So this, the resulting thing now is an honest vector-valued modular form with this weight and with respect to the Weyl representation. So okay, for special maybe, all right. So then that's it. That's more or less it. Yeah. So there are very natural subgroups here for which these things, they are all eigenvalues. So they don't permute them. So actually for each fixed one, this will be actually a modular form, a scalar valued modular form, and then these coefficients cannot grow. So I need to tell you, how do I see FG as such, essentially, and then that's it, right? And let me give you, this is one range. This is range A in theorem 2. Yeah. So these are special cubic fourfolds, right? So if you look at H4, you take the primitive cohomology, meaning the orthogonal complement of everything that comes from the projective space. Yeah, which if X is very general, this is only the square of the hyperplane class, right? But no, actually always is the square of the orthogonal complement of the hyperplane class, of the square of the hyperplane class, right? In P5. So that's what this is. And for the natural intersection product, I declare it to be minus that. Yeah? So then this is a lattice, right? And it's isometric to this lattice. So, and this has signature 220. Yeah? So then the period domain for this lattice, if I do the procedure from before for this lattice, I get an orthogonal Shimura variety. And then my divisor is going to be all those cubics that in this lattice, they admit the lattice of a K3. So there is a primitive embedding from a polarized K3. This primitivity here now is with respect to the polarization of the K3. Right? So this is the locus of special cubic fourfolds of degree D. And then the theorem of Hassett says that, so this thing is irreducible, non-empty, exactly when this happens. And moreover, there is a rational map from FD to CG, right? So this admitting, this is Torelli theorem, admitting, right, the cohomology of a K3 actually gives you back the K3. Right? This is the up to, and there is an up to, yeah, there is an up to at most 2. So it's either 2 to 1 or 1. So and this is a component of this Hegner divisor. So then that's it, right? Then the degree of irrationality of this thing is at most something times this one, because there is a fixed rational map of degree at most 2. Actually, I can put 2 here. And this cannot be more than the degree. Now we are inside a projective variety. So it cannot be more than the degree. And this cannot be more than the degree of this Hegner divisor, which is OD10, because the weight of the modular form is 11. That's it. This is range A. And then, yeah, for the general bound, one has to be a little bit smarter, but not much smarter, actually. I mean, this is the essential idea. Okay, yeah, I stop.
Okay, thank you, Ignacio. I think I will skip clapping hands because in the online talk, I don't know, clapping hands is kind of strange.
Okay.
Roberto, I think you can skip, stop recording.